Hello, class. How you doing? I asked that yesterday. This second time you get to see me in 2 days. That's way more than anybody wants. But it's really my very great honor to introduce Waleed Abdalati today. And he's really had an accomplished career path. Working in the aerospace industry, researcher at NASA Goddard. Do we have a center there or something? I guess we do. There's some small office there that we'd be happy to have them join with us. Where he was the project scientist for the IceSat satellite mission. He was the headquarters program manager for the cryosphere program, back to Goddard, where he led the science definition team for the follow-on IceSat-2 mission. He left NASA for academia at the University of Colorado, and then he was appointed by Administrator Bolden as the chief scientist, and he's now back at the University of Colorado in academia. And I guess there's a note here that whoever wrote this for me that, like me, you have trouble holding a job, so that's it. But he's really, I think the ideal person to talk about this topic. He's spent his career studying the Earth's polar regions, and including spending considerable time there. And I can tell you, having done a little bit in the polar regions, what an exciting area. I mean, it's just kind of a neat area, but it's also very, very important. He received the Presidential Early Career Award for Scientists and Engineers, awarded at the White House. And it's notable that he was the first Earth scientist asked to be NASA's chief scientist. And he was part of the inner leadership team with significant voice for science under Administrator Bolden, and we miss you. I've got to tell you. Now, he made a 2-year commitment to Administrator Bolden, and for some reason, after 2 years, he thought it was better to live in Boulder than inside the Beltway. That's a very strange decision. I can't imagine why anybody would do that. But really delighted to welcome you back. As noted again today, the NASA Earth Exchange under Ramanamani is streaming this live, so we have an audience of zillions, we hope. That's why I didn't tell the usual off-color jokes. But Waleed, welcome back to Ames.
Thanks, Pete. All right, can you hear me okay? I want to pick up on a couple things Pete said. One was living in Boulder versus the Beltway. I used to tell my wife, because we were literally just inside the Beltway, that if you closed her eyes, you could convince yourself the traffic sounded like the ocean. So that didn't sell it for her. The other thing is, you mentioned the places I've worked. A little rundown, and you'll see why I'm doing this in a minute. So I was a co-op student at General Electric. And then after I graduated, I went to work for RCA Astroelectronics, which became General Electric, and then Martin Marietta, and then Lockheed Martin. We're losing companies as time goes on. So I like to say I worked at GE twice. I got my PhD at the University of Colorado, then worked at NASA Goddard, then went to NASA headquarters, then back to NASA Goddard, then to the University of Colorado, and then NASA headquarters. So if you follow that, everywhere I've worked twice. And that's kind of interesting, except it scares me, because the one place I didn't work twice is when I was 16, I worked at Ponderosa Steakhouse. And if you're out there listening, Mr. Crumbach, I'll be back. But I've been very fortunate in some of the things I've gotten to do, and what I've focused a lot of my attention on through much of my career has been the study of the Earth's polar ice cover. In particular, the Greenland Ice Sheet, but also some other things. And I went into it because it was fascinating and it was important. I had no idea what was going to happen physically, scientifically, as time went on. When I first started in this in 1991, it just seemed like an interesting topic to study. And I'm going to apologize to those of you who've heard me speak before and heard this story, but it's worth saying again, I think, for those who haven't. I fell in love with NASA when I was about 5 years old, and I remember very vividly when Apollo 11 landed on the moon, and my friends and I used to play Apollo astronauts, and my best friend, his name was Matt, we used to go to his house, and we'd go to his kitchen, and we'd drink some Tang, and then we would walk out to his shed. You know, we like we were in slow motion, like we saw on TV, holding our helmet and doing this walk to our Apollo capsule. And, anyway, we'd walk out to the shed, do our slow motion walk, we'd get in, we'd shut the door, and we'd do a countdown, and we'd bang ourselves violently against the walls of the shed for a while, and then we'd stop. You know, we will have landed on the moon, right there in Matt's backyard. And we'd open the door, and we'd step out. You know, we were on the moon, and now I tell people it was Matt's house, Matt's yard, Matt's Tang, Matt's shed. Matt was Neil Armstrong. But I got to be Buzz Aldrin, and that was fun. So I'd wait patiently, and then I went out, pretend to take his picture, he'd salute. But this is true, kids are mean. There was a third kid who sometimes wanted to play with us, and we let him be Michael Collins. And we would not let him out of the shed. We would just... We'd go play, we'd come back, tell him about it. He got to drink the Tang, though, so it wasn't all bad. But as I got older, so this is the view many of us, you know, who fell in love with NASA early on remember. But as I got older, this was another kind of picture that NASA revealed to me, and it really did change my life and my career. And I started doing research in this part of the Earth. And these parts of the Earth, what I love about them is they're just incredibly pristine. You know, to go to a place that nobody's set foot before, not unlike Matt's backyard in my years earlier, but where no man has gone before, untouched, really felt like a privilege and gives you a different kind of appreciation for the planet. These places are also very, very rugged, very raw, very majestic. They're huge. You know, it's amazing to be in a tent and think about, you know, there's ice for hundreds of miles in any direction, perhaps 1,000 kilometers in another direction. So this was work. You know, you guys here probably have some commuting issues. These were the sleeping tents. This was the kitchen tent. That was the work tent. My commute was wonderful. Sometimes I'd walk, sometimes take Skidoo, and this guy here, this guy snored. He snored really loudly. And I swear, if this picture had been taken 2 days later, this tent would not be in it. It was a beautiful place to do work, and really, really spectacular. I love this picture, I hate this picture. Two of us are standing side by side, took the same photo, and Nick's came out so much better that I show his, and I have to give him credit. Price of a cheap camera, I guess. But these places really are beautiful, really spectacular. And they're changing. And they're hugely important for the Earth system for a lot of reasons. I'm going to give you the big three. The first is sea level rise, the amount of ice locked up in the Greenland Ice Sheet, the Canadian ice caps, Alaskan glaciers, certainly Antarctica. Tremendous impact, tremendous potential to raise sea level. The sea ice cover serves as a barrier to energy, to momentum transfer between the ocean and the overlying atmosphere. Traps heat. The formation of that ice cover affects ocean circulation. And the fact that it's white provides what we call a positive albedo feedback, which some of you, I'm sure, are familiar with. The sun shines, it reflects off the white ice. And as that ice starts to melt, rather than be reflected, it gets absorbed. And that absorption leads to further heating of the ocean, which further melts the ice, and it's a self-compounding process. So these regions help keep the planet cool, but as they diminish, the planet heats up more rapidly. But I mentioned sea level. Greenland holds the equivalent of 7 meters of sea level. I'll get to this in a little bit. It's not so much that all of Greenland is going to disappear, but a meter sea level rise is hugely disruptive. These are the areas affected by a meter sea level rise worldwide. And if I bring it a little closer to home, although This is more an East Coast talk, I guess. But the West Coast just isn't quite as dramatic when it comes to sea level rise. You can see the implications of simply 3 feet are staggering. Now, in some sense, it's not fair. This is sinking anyways, the Mississippi Delta. The removal of sediment that's not being replenished. Even if oceans weren't to go up, these areas would be affected. But certainly the eastern seaboard, southern Florida, I showed this figure. I gave a talk to a retirement community on Sanibel Island in Florida. And I put this up, and there was a gasp, like a scary gasp, because these people, it was a retirement community, so when people gasp, you worry. But nonetheless, the implications are staggering. This is 1 meter sea level rise. Okay? And if we look at our past, 1 meter, sea level has gone up. So, 1 meter sea level rise, that's not outside the estimates really by the end of the century. There's a range of estimates, but that's certainly on par with some of them. So 1 meter in a century versus 50 millimeters a year we've seen in our past. Okay? So 5 meters, is that right? Yeah, 5 meters in a century, oceans have gone up in our past. Now, to be fair, there were huge ice sheets blanketing much of the northern hemisphere, so we don't have the potential for that rapid a rate of sea level rise. But the point is, ice can change quickly, and the implications for sea level have historically been quite substantial. It's something we got to pay attention to. So I work with remote sensing observations for a few reasons. This is one of them. It's just hard to make measurements. This is a radiometer measuring the amount of incoming sunlight. We've got some thermometers here. We've got a sonic depth sounder ranging the depth of the snow. It's just hard to make these measurements. Access is costly, difficult, and dangerous. Now, if you look closely at this picture, I say this to my kids, what's wrong with this picture? My 6-year-old says, Dad, it looks like the wheel of the plane isn't attached to the plane. That's true. Or for the aerospace engineers who study propellers and lift, you can see the problem with these propeller and integrity of the... I can show this because people were not hurt, but there really have been tragedies in the collection or deployment of our Arctic and Antarctic field campaigns. But this is the main reason. This says it all to me. Context, scale, and perspective. Okay, this is why we use the satellites, we use the aircraft to make these measurements, because turning information that you learn here into something meaningful about this is a real challenge. Now, the space-based capabilities enable us to do this really in remarkable ways and allow us to look at the interactions of the system. Now, I'm sure I'm preaching to the choir, at least in this room, but for those of you out there, maybe it's something you didn't know. So when it comes to ice sheets, the big questions we ask are how and why they're changing, and how will they change in the future? What are the implications for sea level rise? And this is a slide that I call Ice Sheets 101. It's pretty intuitive. An ice sheet grows when snow falls. It shrinks when the surface melts or when there's calving at the margins. We also have redistribution, we have surface runoff, we have runoff on the underside of the ice, we have melting on the underside of the floating ice. But in a nutshell, this has been the question for a lot of years, which we've got a handle on now, is warming temperatures increase melt, increase the flow rates or the calving rates, and they increase the precipitation. So it's conceivable that at places like in Antarctica, where the temperature is very far below melting, that the increase in precipitation will actually offset these other phenomena. So for a lot of years, we were simply asking, will the ice experience a net growth or a net shrinkage in a warming climate as these factors competed with one another? Spoiler alert, the shrinkage wins. So there are several ways we attack this. One is what we call the flux method or input-output, where we look at what's falling, what snow is falling upstream, how much melt is occurring in the margins, and what the discharge rates are. And what the discharge rates are, and we just add it all up. It's just an arithmetic problem. Well, the arithmetic's easy. The acquisition of all that other information is very hard. You're looking at surface flow vectors in this particular image. Another approach is with altimetry. I apologize, you can't see the satellite, but you can see the beam. This is an animation of the ICESat mission. We simply measure changes in topography day after day, week after week, month after month, year after year, and we accumulate that to learn where the ice is growing, where it's shrinking, and turn that into a mass balance assessment, a sea level contribution. This has, one of the things this provides too is there is a topographic fingerprint to the nature of change. If an ice sheet is shrinking because glaciers are speeding up, that has one topographic signal. If it's shrinking because there's more melt, that has another. If it's shrinking because there's less accumulation, that has another, which I'm happy to talk about offline if anyone cares to know more about that. And then the third is the gravimetry. I suspect most of you are familiar with the GRACE satellites, but it's 2 satellites to fly along, one behind the other. And when it approaches a gravity anomaly or a different gravity field, they separate. The first one goes faster if there's more mass underneath it, and then it slows down when it passes that. The second one speeds up and catches up to it, and that separation between the two over the ice masses tells us something about the mass of the ice beneath it. So over time, we measure, are they getting farther and farther and farther apart? Each time they pass over the ice sheet, which would mean the ice is growing, that gravitational perturbation to the orbit is getting higher and higher, or are they getting closer and closer and closer together, which means the ice is shrinking. We have a number of tools to help us get not just at that assessment, but at the underlying mechanisms. We can track the motion, we can track the volume and mass change, the temperature characteristics, the surface melt, the spatial extent of the ice, where the calving fronts are, the snowfall, and the grounding lines, where the ice comes afloat as it flows into the sea. So I'm going to focus on Greenland for just a little bit, where I've done a lot of my work. And the characteristics of Greenland, 7-meter sea level equivalent stored in this big slab of ice. There's a lot of surface melt in the summer. This shows 2005 in red and pink, but sort of the average melt characteristics. So about half the ice sheet experiences some melt on the surface. And I put slippery when wet, and I'll explain that in just a little bit. So if you look at this place here, this is called the Jakobshavn ice stream, the fastest glacier in the world. This is the calving front. For perspective, this is about the size of a football field here. And through hydrostatic equilibrium, that's only about 1/10 of the mass of the ice. It's about 9 times, 10 times deeper. It's actually a little less because the geometry is a little different below the water than above, but nonetheless, it's a lot of ice. And this was a picture I took years and years ago, my first time in Greenland, from a helicopter. And again, for perspective, the helicopter was about the size of this dot to take the picture of the calving front. Now, when these things calve, it's really quite remarkable. So, how many here have seen the movie Chasing Ice? Okay, so you've seen some unbelievable, now I'm embarrassed about this picture, but you've seen some unbelievable photographic documentation of ice changes. This is just a video, for those who have not had the benefit of seeing it, of what it looks like. Remember, this is about the size of a football field, just what's above the water, spills into the sea, overturns it. You can see the difference between the melange, the unattached ice, and the more rigid but still floating ice. This is where the rubber meets the road, so to speak, or the ice meets the water, or whatever, but where the heart of rapid change in ice occurs. And this is an animation that's going to tell you a little story about what's going on in the ice. And you're going to zoom into the Jakobshavn ice stream here again. And remember I said, I think I said, it's the fastest glacier in the world. Historically, has moved about 7 kilometers a year. So with our satellites and aircraft data, we watched a story unfold. So we're zooming, this is MODIS imagery at the moment that you're looking at. We're zooming into the ice stream. Now it's MODIS imagery. You got the margin, you got sediment discharge, you've got these melt ponds on the surface, which I'll talk about in a little bit. This is the calving front, where the icebergs break off into the sea and flow out to the sea. This is floating ice. This is what we call the grounding line, where the ice upstream of that is resting on land. So we're going to zoom into the ice stream. So you got the icebergs, the calving front. These are flow vectors derived from satellite imagery. You see the main ice stream, the tributary, what we call drawdown here, the entrainment of ice being carried out to the sea. And again, these melt ponds. Now, this front was stationary for about 50 years. It moved back and forth as the ice flowed. But then in 2001, or shortly after actually, it began to retreat about 1 kilometer a year. So here you see, it's actually a little more than 1 kilometer. This is more like a mile here. Progressive retreat of the ice. And what happened is, as this retreated, this buttress to the flows, kind of like a plug, a cork in a bottle of wine, was removed, and these glaciers sped up. They doubled their speed to about 14 kilometers a year, and I think I'm going to try and stop it, to about 14 kilometers a year. That's about 5 feet an hour, where if you just stop and watch it for a little bit, you can see it. If you stand and you look at a rock, you can see the ice move through your line of sight. We didn't think glaciers could go this. This was the fastest glacier in the world. So for it to double its speed and maintain that for years was really remarkable, something the satellites had revealed to us. And then what you see here is elevation change derived from ICESat, where you have slight thickening, because it snowed more in the 2003 to 2009 period where these observations were made. This actually grew. White didn't change. Blue and purple is thinning. And I mentioned the topographic fingerprint of change. This bullseye-like feature, that's indicative of glaciers speeding up. You remember that entrainment, that drawdown area? That's pulling ice in from off of the main ice stream and causing a slumping, causing a decrease in thickness of the ice. This is a net loss of ice. And what we've seen over time is it isn't just Jakobshavn, but this glacier actually slowed while this ice backed up and thickened. But all along the coast, and on the east coast as well, these glaciers have begun speeding up. This is why I say, are we waking sleeping giants? You know, this ice has sat there, behaved a certain way for a long time, and now as it's getting warmer and these buttressing floating ice tongues are being removed, the ice is speeding up, flushing more ice into the sea. And what this does is it shows that it's not simply, you know, it doesn't take centuries like we used to think for heat on the surface to make the ice warm, to make it flow a little faster. You know, we used to think the response time of ice sheets was decades, centuries, or even millennia to today's perturbations. Turns out it's minutes and hours in some cases. It's a structural coupling. This is just the record of calving front up through 2009. And the big question really is, what does it look like underneath? And what you see here, everything in blue is below the bedrock, below sea level, and everything that's not blue is above sea level. The more brown it is, the higher it is. So this Jakobshavn ice stream is actually a conduit to several meters worth of ice, as is the Petermann Glacier, right? And another glacier with a Norwegian name I can't pronounce. So there's sort of avenues for this ice to flow out to the sea rather rapidly. So it's got our attention. This is what we're trying to understand. So the question is, are these points of instability? We're trying to figure this out. Many of you may be aware that in 2012, Greenland experienced what we call a record melt. I use that term loosely because the satellite data have only been around for 30 years to track this melt, so a record in 30 years isn't that impressive. But when you see how different this is from all that preceded, it really is quite remarkable. So this is sort of the area that would be covered in a slightly higher than average melt year. White is not melting, reds and pinks are melting. The degree of redness is how confident we are of that surface melt. For a couple days in July, 97% of the ice sheet experienced surface melting. Now, I gotta stress, this is a meteorological phenomenon, not a climatological phenomenon. This happens. The ice cores show that this happened about 120 years ago, happened a few hundred years before that. History is punctuated with events like this, and it has to do with atmospheric, sort of a perfect storm of atmospheric circulation bringing warm air from low latitudes, the radiative characteristics being just right to allow melt. So it's in our past. But what's different is if we look at the melt record, and this is just a melting index, sort of a fraction of the ice sheet melt cover. The microwave radiometer has a very distinct melt signal. When snow starts to melt, it emits microwave energy more efficiently. We tracked this in time, and in 2012, the melt was far greater than the years that preceded it in the satellite record. So although this is a meteorological phenomenon, it's happening against the backdrop of a changing climate. So what does this mean for next year and the year after that? Well, the likelihood of this kind of melt is quite a bit higher than it had been in the single year events we'd seen in the past. So stay tuned if you're interested. If you're not, go to sleep. I mentioned melt lakes, okay? And again, if you've seen Chasing Ice, you've seen imagery of how beautiful and really just a spectacular shade of blue these things are. But they punctuate the ablation zone of the Greenland ice sheet. There are undulations in the ice. So when the water melts, it collects in these undulations and creates these lakes. And if you look, there are sort of cracks, the crevasses, and what we call moulins, or openings in the lake. Now this meltwater, there's a hydrostatic pressure. It's heavy water. It's water, so it is heavy, I guess is the way to say it. Either pries open these crevasses or flows into these tunnels, as you can see here, just straight down into the ice, through as much as a kilometer, even more, of ice to the bottom of the ice sheet. So this was actually from the cover of a paper that we had in Science a few years back. And you can see these rivers of water running into these holes, and if you stand and look down, this is what you see. And that ends a kilometer away at the bottom of the ice. So I want to call your attention to this picture again. This is what I like to call evidence of academic hierarchy. I think you have, the college professor standing back a certain distance, and progressively you have your PhD student, your master's student, some undergraduate intern with. I say that because the back is to the flow, and this. I mean, that's. I wouldn't do that. And of course, your postdoc determined to find his or her own way, asserting independence. But if you look at these melt lakes, I mentioned the water flows to the bottom. It looks something like this. Enough hydrostatic pressure builds up, and the water finds a way into the ice, to the bed, flows along the bed, and makes the ice slippery. And so what we've seen is the ice doubles its speed, in some instances, in the summer. So the wetter it gets, the thicker this water layer, the faster it can travel in the summer. So there is some concern, and it's turning out, it doesn't look quite as bad as we had thought, but we're still figuring this out, that more meltwater would make this more slippery and result in more acceleration of ice in the summer, and again, contribute to sea level rise. I'm going to switch hemispheres on you now and look at Antarctica. And this is an image of the Antarctic bed. If you were to remove the ice, the whites and reds are above sea level, the blue is below sea level. So in this case, remember what I showed you about Greenland with those conduits being potential sources of instability because they provided access to the rest of the ice sheet. Here we have tremendous access to all of that ice by what we call ice that's grounded below sea level. So Antarctica has the equivalent of about 60 meters sea level. Temperatures well below freezing, so melt isn't quite so much an issue except on the peninsula. The West Antarctic ice sheet's about 3 meters sea level equivalent. That's grounded below sea level, rests on a soft bed till. It means it's very deformable and the ice can sort of slide across it more easily than if it's frozen to bedrock. So we ask, is this unstable? Okay? And the point of instability, or the most likely point, is what's been called the weak underbelly of the West Antarctic ice sheet, the Thwaites and the Pine Island glaciers. And if you look at Antarctic temperatures, a lot of it's been warming around the perimeter, but there have been some areas of cooling. I don't have an updated version of this map, but the trend is essentially the same. Some areas of the ocean cooling. There are complex circulation patterns associated with this. But I talked about the weak underbelly of the ice sheet. What's happening is that this ice, this floating ice, is melting, is removing this restraining force, and this is starting to accelerate into the sea. Now, I asked the question about instability. What does instability look like? Well, the floating ice melts, the glaciers speed up, they get thinner, and they lose mass. And when we look at the GRACE data, we see this area losing quite a bit of mass. We look at the altimetry, it's getting thinner. We look at the velocity data, it's speeding up. And when we look at the visible and radar imagery, this ice is thinning. This floating ice is shrinking. So I don't want to use that to say, head for the hills and instability is well on its way, but certainly the behavior we're seeing is consistent with an unstable beginning of the breakdown of the West Antarctic ice sheet. If you look at the Antarctic Peninsula, some of you may have seen this. This is really a dramatic illustration from the MODIS imagery. This is January 31st, 2002. I'm just going to loop through a few weeks. This ice, 10,000 years old. And I forgot which New England state it's the size of. I think it was Rhode Island. It's whatever state they use. Connecticut, Rhode Island, take your pick. It's a lot of ice. That's what they say. The standard unit of measure is small New England states when it comes to icebergs. But this was floating ice. Doesn't affect sea level directly, but indirectly, again, it's this buttressing effect. This glacier accelerated 8-fold once that ice collapsed. 10,000 years of ice, hundreds of feet thick, gone in 6 weeks or 5 weeks. This glacier accelerated 8-fold. The glaciers that fed the remnants of the Larsen ice shelf didn't change at all. We had the perfect control experiment. We only perturbed one variable, the structure. Okay? And if you look at the Landsat imagery, what you see is water-filled crevasses. This is why it could break up so quickly, because there's water in these crevasses and it all just kind of shattered. Again, it's a mechanical process here. I would be remiss if I did not mention glaciers and ice caps, So get away from Greenland and Antarctica for a while. And this paper just came out actually last week in Science. The period is 2003 to 2009 using GRACE data, ISAT data, field measurements. And this just shows where the ice is shrinking. It's shrinking everywhere on mountain glaciers. But for perspective, this is gigatons per year of change. 360 gigatons per year is 1 millimeter per year of sea level equivalent. So glaciers and ice caps are responsible for about, at least in this time period, a little less than 1/3 of the current sea level rise rate. And actually more than Greenland, quite a bit more than Antarctica. So at the moment, at least for this period, these glaciers and ice caps, which are more temperate, are contributing more to sea level rise than the other two ice sheets. The difference, though, is there are limits to how much these will contribute. You know, less than a meter, if they were all to go away, less than a meter of sea level rise as opposed to 60 meters in Antarctica, 7 meters in Greenland, and the potential for much more rapid change from these ice sheets. So we got to look at all of them, or both of them, I should say. I'm going to move on to sea ice real quickly. I won't spend quite as long. This is your obligatory photograph of polar bears. Can't talk about sea ice without polar bears. These are the tools we use to understand sea ice, the remote sensing tools. We look at the motion, deformation, reflectance, thickness, spatial extent, the concentration, the temperature characteristics, using different tools. But every year, ice goes through this process of growing in the winter, shrinking in the summer. And if you just look at the minimum, that's the maximum there. If you look at the minimum right there, that's the thick multi-year ice. This is stuff that survives the summer melt season. It's hardy. And what happens to it tells us quite a bit about the state of the Arctic as a whole. This is the trend in multi-year ice cover. I apologize, I probably should have started it at 0 to give a better representation. But suffice to say, that when we look at the record, the start of the satellite record in 1979, we're below half as much ice. And it's been a fairly steady downward trend. This is what we call the minimum, the perennial ice cover in 1984, which is an average year. If you look at 1984, just so you know, I didn't cherry pick. Well, actually, it's an above average year. I guess I did cherry pick, but it's close to average. This was 2012. Big changes underway. And if this is the average, actually, from the satellite data as compared to the minimum in 2012. So if we look at this, one thing you should note is in 2007, the Northwest Passage became navigable. This area in here, which is, you know, sort of a fabled shipping route, and you know, for years people have tried to sail the Northwest Passage. Well, in 2007, a 76-year-old retired hog farmer and his wife, he's from Minneapolis, sailed it in a boat called the Cloud 9. They posed, they got their picture taken, the happy couple. And if you bring this up to someone who's pretty knowledgeable, they may tell you, well, that's not new. It was done in 1903 by Roald Amundsen. And that's true, kind of. It was done in 1903, 4, and 5 by Amundsen. And I like to think that Amundsen is looking on at this happy couple saying, you know, when I did it, it was a much different, you know, experience. And the Cloud 9, I think his boat was called the What Was I Thinking, or This Sucks, or actually it was called the Fram. So it's a different time. Okay? And we're pretty well on our way to what may be an ice-free Arctic in a matter of a couple of decades. And human civilization, as far as we know, has never known this. The implications for weather, the implications for climate, really are not clear. And what's a little scary to me is these are all our best models telling us what the ice will do in the future. And the red is the observations. If I roughly, if I capture the variability of the models, it doesn't take long to see maybe our models have some problems and we need to fix them. Reality certainly looks different than what we're observing, what we modeled. But it turns out that one of the challenges with models is they don't do a good job or have the data to account for thickness of the ice. the thinner ice will disappear more rapidly. It's more vulnerable. So with ICESat and the upcoming ICESat 2, we can estimate thickness from the freeboard height. We have a laser pulse on ice, a laser pulse in water. We take the difference and we can figure out the thickness characteristics. And with ICESat, we did this for, this is comparing 2003 to 2007. And what you see is the thin ice is gone, the thick ice is thinner. Or we can use the signatures of, the microwave signatures of the ice, or we can classify multi-year ice and first-year ice. And what we see is a much younger, thinner ice cover. Generally, we think of younger and thinner as a good thing. When it comes to ice, it's not. It's a bad thing. Now, the Arctic comprises, well, actually, I'll skip over that. Well, no, I'll play it. It's fun to watch. So the Arctic is changing, and the Arctic interacts a lot with the ocean system, with the atmospheric system. It's not simply the cryosphere in isolation. And I would be remiss if I did not point out that ice in Antarctica is growing on average. Some areas it's shrinking a lot, but on average, there's a slight increase of about 1% per year, as compared to, you know, the multi-year ice cover decrease of close to 10% per year. Almost done here. I do want to take a second, though, to talk about the climate record that's preserved in ice. Most of you are aware that ice cores trap bubbles, trap past atmospheres, and we can study them. We can study their content. And this is a graph showing temperature characteristics. Now, today is here, and we work backwards in time. So what you see is here we had the medieval warm period. Yeah. The medieval warm period right here and the little ice age right here. This perturbation, the medieval warm period, the Vikings settled Greenland. It really was green. It was kind of a mossy. It wasn't a joke to get everyone to run to or stay away from Iceland or whatever, but it really was green. And this perturbation drove a people off a land. But if we go further back in our past, things had changed much, much more dramatically. Now, if we go way back, 400,000 years, and the story is about the same for 800,000 years, actually, we see variations in carbon dioxide. This is from the ice core record. We see temperatures have changed, carbon dioxide has changed, CO2 is in blue. And here we are today. Nature kind of doesn't do this unless it's happening geologically. If we go back many millions of years, we may see more carbon dioxide in the atmosphere. But what's happened is historically temperatures have gone up and CO2 has risen as a result of that. Today we're in a different environment where the CO2 has gone up and temperatures are lagging that. Now, Richard Alley, a colleague of mine, does a great job explaining this. It's like your credit card debt. You can charge up your credit card really fast, but because there's interest, it takes you a long time to buy it back, to pay it down. Then you can charge it and pay it down. Charge it, pay it. So once there's carbon dioxide in the atmosphere, the recovery is much more challenging. Well, now we're in a time where we're putting the CO2 in the atmosphere first. So it's different. So when we look at this, particularly this figure, I can't help but just think we're in unfamiliar territory. And what I study, the world's ice cover, is really responding dramatically. And how we as a society respond to that, or how successful we are in the face of those changes, really depends on how big the changes are, how fast they come, and our ability to anticipate them and understand them. Well, these first two are sort of where policy comes in and decisions we make to affect the rate and magnitude of change. This is where the work that a lot of us do comes in, trying to understand what's going on and why. Now, there are different responses to this threat, phenomena, situation. This is one. This is my friend Ian Jockin. I'll give you a second to think of your own joke. I won't tell you one. This is another. And you know, I'm proud to be part of an enterprise, as I hope you all are too, that's trying to do this, trying to observe and understand. My apologies to the aircraft people among you. I'll just tell you, there are a whole bunch of planes in here. You just can't see them because of the eclipse. But here's something for the aircraft people. Some of you have seen this, I'm sure. But this is flights throughout a day, so superimposed over the Earth at night. And I love this. You see, you know, night's coming, all the flights going to Europe, and then as daylight comes in Europe, they'll start to move out from London and Paris and places like that. And I show this picture because a lot of times people will say to me, I just don't see how humans can make a difference on our planet. It's so big, you know, it does what it does. I don't see how humans can affect it. I look at this and I don't see how humans cannot affect it. This is a tremendous fingerprint on the planet, and it's just one aspect of what we do. So I'm going to leave you with a quote from our friendly Roald Amundsen. I don't think he was as grumpy as he probably looked in that image. I love this quote. One thing about Amundsen, I mentioned him in the context of sea ice. Amundsen was the first person to successfully make it to the South Pole. 11 days later, Scott from England came in second in the race, which is a terrible thing to come in when you're racing to the South Pole. But his party died tragically on the way out. And Amundsen's comment about that was this: I may say that this is the greatest factor, the way in which the expedition is equipped, the way in which every difficulty is foreseen and precautions taken for meeting or avoiding it. Victory awaits him who has everything in order. Luck, people call it. Defeat is certain for him who has neglected to take the necessary precautions in time. This is called bad luck. Now, I was tempted, I couldn't bring myself to do it, to have the next slide be Clint Eastwood pointing a gun saying, do you feel lucky? But I think this quote is very powerful, it's very profound. And if you think of the journey we are on as a civilization, as a society, I don't want to leave it to luck. Thank you.
You use satellite altimetry data to measure the volume of ice sheets. As these ice sheets melt, are these measurements somewhat confounded by the continental rebound underneath, and how do you correct for that?
Yeah, we do have to adjust for that. It's not much, you know, it's millimeters as opposed to many meters of change. But when you average it over the area of an ice sheet as a whole, that's a large area times a small height, makes a meaningful volume. So we account for that using models of post-glacial rebound. And those models are based on gravity data, GPS data around the perimeter of Antarctica, the perimeter of Greenland. So they're pretty good, but that's part of the uncertainty calculation. So yeah, it's, you know, the ice you're losing is actually more than it looks like you're losing because it's kind of coming at you to begin with, but it's a small amount.
Do you have the same problem with depressing ocean basins?
The question is, do we have the same problem with depressing ocean basins? Yes, and again, we try and model that the best we can, but that feeds into the error calculation, uncertainty calculation.
I've read that the IPCC reports so far in projecting sea level change have not taken into account ice loss. Is it they literally didn't, or they just assumed that we'll take the most certain data we have, which is underestimated?
Well, it's not that the IPCC doesn't take into account ice loss. What they say is these dynamic processes, these nonlinear, unstable processes, we don't know enough to quantify to credibly project based on them. So what the last IPCC assessment did was give a range and then said, but there is this dynamic component which could be quite large. We're not able to quantify it sufficiently to include it in this report. Keep an eye out for it. Okay? Yes?
Thanks for the presentation. I was wondering if you could speak briefly about the impact of freshwater from Greenland coming into the North Atlantic and shutting down the Gulf Stream conveyor belt and that change on climate in Northern Europe.
Yeah, that's certainly a possibility that's out there. So we have freshwater input to the North Atlantic from Greenland, and the way the system works now, as how does it work? As sea ice forms, it rejects salt into the ocean, and you have a density structure for a little while where there's more dense water on top of less dense, so it sinks, displaces the water around it. So actually, the bottom water in oceans all over the world largely originated in Antarctica and in the Arctic. If you freshen the top, then you have a stable stratification of density, and that sinking and overturning does not occur. Now, and what that does is, because the water, it's like you put your hand in a bathtub or in a swimming pool at the top and you push down, what happens? You draw water toward the space left by your hand. And this is believed to be sort of what, in very simple terms, what sets up the Gulf Stream that keeps Western Europe warm and the coast of the United States warm. So the big question is, well, what happens if we suppress that? If we keep a density stratification that's stable, that does not permit this this sinking to happen? Certainly the likely outcome, if we do suppress it, is a shutdown or change, at least, in the Gulf Stream. The big question for me, though, is, how much fresh water does it take to make that happen? What are the implications of that? And that we just don't know.
Yeah, that's sort of my question, is what's the scale that's necessary? I mean, does Connie Stephan contribute to that with his loss of sea ice as well?
Well, a little bit. I mean, as much as any of us are all sort of trying to figure out what's running off where. But this would probably be a better question for Jim Hansen than me, but I don't think we have a sense as to how much it would take to shut that down, and if that's something we're going to expect to see in the next 100 years.
The issue, though, is that if it does shut down, then it changes the climate
yeah.
parameters hugely in the Northern Hemisphere. And so does that cause a negative feedback against the...
It would make the Atlantic fringe of the Northern Hemisphere colder. To me, the bigger question is, what does the loss of sea ice, which we know is coming, well, we're pretty confident is coming, what does that do to the jet stream, or to the atmospheric characteristics? And that we just don't know.
Yeah, on the graph you showed from the sea ice cores showing that temperature and CO2 tracking together over the last several 100,000 years. I think you indicated that the CO2 increases and decreases follow the temperature changes.
Temperature's red, carbon dioxide's blue.
Okay, so are you saying that it's the temperature change that drives the CO2 change?
So what drives the temperature change is the orientation between the Earth and the Sun. The tilt of the axis, the proximity to the Sun in summer, Northern Hemisphere summer versus Northern Hemisphere winter, and things like that. So there's a strong 100,000-year scale, there's a 40,000-year scale, there's a 20,000-year cycle, I should say, not scale. So that makes the Earth warm or cold. When the Earth gets warm, there's a release of stored carbon dioxide from the soils, from the oceans, and that's the interest on your credit card. So because this is geometric, if there were no greenhouse effect associated with it, if it was just the moon doing this and you're measuring the temperature, you should have symmetry. It should come down as fast as it goes up. But because when it goes up, there's the release of gas that retards the return to the base state, then the decrease is much slower. There's an asymmetry than the increase.
Thank you.
Yep.
I have two actually online questions. The first one is very specific. It's related to the difference when you're comparing the ice shrinking from satellites compared to the models. So the question is, how sure are you that measurements the measurement uncertainty is better than those from climate models? That's the first question.
That's a good question. Because they're different. What makes me think that the uncertainty surrounding this, because I didn't show bars for that, is any better than that? A couple things. I guess in the simplest sense, seeing's believing. I mean, the signature of ice presence in water is so clear that there's probably no way we're off by more than the thickness of that line or double the thickness of the line itself. These are ensembles where we take our best estimates of the physics, and try and reproduce. These are much more complex, so there's inherently quite a bit of uncertainty in them. And this bar, this is really my guess at the 1 sigma range, but you can look at the spread of the models. It's instructive that none of them capture what happened to the ice, none of them. And I don't remember the uncertainties in our sea ice estimates, but it really is pretty tight because the signature is so clear.
And there's another one. It's more generic. It said, what do you think the safe concentration of greenhouse gases?
Safe?
Yeah.
Boy. I'll pick 350. I mean, that's if you look at the history, it's been about 280. But this, there weren't people living here, and actually, you need a certain amount of greenhouse gas to keep the planet warm and habitable, right? So you want some. I don't know. That's a job for the modelers to say. I mean, I don't know. I can't answer that. But what I will say is, whatever the answer is, it's clear that the farther we get from that, the greater the challenge we face. So whether I say it's 300, 350, or 400 where we are today, we're on a trajectory that's taking us away from, I don't want to say recoverable, but from the state, from the conditions under which human civilization has evolved.
Hi, thanks for the presentation. I'd just like to know, just to follow on to the predictions, how the modelers or certain prediction companies are taking into account the increased activity in the future in the Arctic, in particular when the ice melts and more shipping routes become active, and then we have resource extraction as well that might become available in the future. This might net overpopulation in the Arctic in the future. How is this going to increase the temperature change and the climate change in the Arctic?
Are you asking how that will increase?
Well, they've already talked how to change it, but how are the modeling people taking that into account?
I don't know how they're taking it into account because I think everyone's doing it differently. But the things that need to be considered are, one, the added pollutants that are put directly into the Arctic atmosphere, but two, the darkening of the snow and ice surfaces. As this is soot that you can imagine these diesel-powered vessels going into the Arctic. Well, eventually that stuff's going to fall out, and that darkens the surface, which adds to this albedo feedback. How the modelers handle it, I don't know. But I do know that you're talking about traffic, which will break up ice, because you go up there with icebreakers, and the more broken up the ice is, the easier it will be to melt or be carried down to warmer waters where it will melt. It will be the inherent pollution itself that's put into the atmosphere and the radiative characteristics of that, and it will be what precipitates out or what lands on the surface that darkens the surface and causes more energy absorption then. Quantitatively, though, I can't speak to the implications, only qualitatively.
Thanks.
Okay. I think we ought to end that with another round of applause for a great talk. And I remind you that there are some refreshments in the lobby of Building 200.
Thank you. I appreciate it.